In this video, we're going to look at energy levels in atoms and line spectra. There are two kinds of spectra, that is emission spectra and absorption spectra. Emission spectra result from emission of energy. The line emission spectra reviews colored lines against a dark background. So we can just say bright lines on a dark background. Each line is a particular wavelength of light emitted by the source. To view this, we use what is called a spectrometer. Line spectra obtained from atoms, e.g. hydrogen and neon at low pressure, in discharge tubes and substances heated in a blue Bunsen flame. Each element produces a unique spectrum. In the sodium line spectrum, the two yellow lines of wavelength 589.0 nanometers and 589.6 nanometers are more intense than the rest. There are four visible lines in the hydrogen spectrum. And then we do have what's called continuous spectra. Continuous spectra are produced by hot solids and liquids, e.g. tungsten filament lamp. The sun produces a continuous spectrum as well. The temperature of the source can be determined from its continuous spectra. I have something to show on this. So this person here is obtaining the sodium line that we're talking about. So using sodium bicarbonate, solid sodium bicarbonate. So as you can see, this is the dark line that you see in between there is due to the absorption spectrum of sodium. So what it means is this is a dark line on a bright background. Sodium absorbs that color which is characteristic to it. So that is the light that we see there. And then we have the line emission spectrum to show. This is for hydrogen. Now if we then view it through a diffraction grating or a spectrometer, you'll be able to see bright lines from a dark background. As you can see, this time the background is dark, and then we are going to see bright lines from the emission of spectrum of hydrogen. So there we are. We're going to have the dark blue one, and then we've got the turquoise blue. This could be violet. Let's just say this is the violet, and then blue, turquoise blue, and then we do have this one which is sort of like bright red. So these are the lines that we can see within the visible spectrum. In the electromagnetic spectrum, this is what we can see, what our eyes can see on the spectrum of hydrogen. So it has two lines there, that is this side and that side, and this is where the hydrogen is emitted. So the background was dark, but then we have these lines that represent the emission spectrum of hydrogen. Now if it was an absorption spectrum, then we would start off by having something there. We heat up the gas, and then it's going to have a spectrum, a bright background, and then the hydrogen is going to absorb those colors that are characteristic to it. So these were going to appear as dark lines if it's an absorption spectrum. If it's an emission spectrum, they appear as bright lines as they are. So this is an emission spectrum. So this is what you can see from there. This is the emission spectrum of hydrogen. If we are to do an emission spectrum of neon, we are going to see very bright orange reddish color. That is neon. So those neon lights that are used in Christmas celebrations, you see the bright orangish reddish color. So in this case, this is the line emission spectrum of hydrogen. Right, so band spectra, these are produced by the molecules rather than single atoms. So three things that you need to tell apart. The continuous spectrum. Remember I said continuous spectrum mostly from solids and liquids, that is. And then we have line spectra which come from gases. We can have line spectra from gases when we use the diffraction grating that we talked about. Band spectra now produced by molecules rather than single atoms. So when we have a mixture, we have molecules now. Instead of atomizing, we are just having molecules. So we get band spectrum. So we'll look at band spectrum when we look at the band theory. In this video, we're just going to concentrate on line emission as well as absorption. So the line emission spectrum for sodium, this is what we observed. So we observed it as an absorption spectrum. Remember, the visible spectrum is from 400 to 700 nanometers. So these are the lines that we can see from the line emission spectrum of sodium. So the background will be dark, but then we have these lines like sodium emitting this from its spectrum. Similarly, the line emission spectrum of hydrogen in the visible region, we saw this in the video, that is the red one, the green one, the turquoise blue, as well as the violet one. Now, looking at the absorption spectra, these are due to the absorption of light by a sample. Absorption line spectra consist of dark lines against a background of the continuous spectrum. For example, when light from tungsten filament lamp is passed through a sodium flame as seen through a spectrometer, two black lines appear in place of two strong yellow lines. We have seen that in the video. Dark lines where there was that yellow line, so which means sodium absorbs that. So only that wavelength is absorbed in the continuous spectrum that you see. Electrons in the sodium atom absorb the energy from the incoming radiation and then re-radiate it in all directions. The energy traveling in one direction is spread about and compared with the rest of the spectrum. These wavelengths appear dark. Now let's look at Bohr's quantum explanation of this. The origin of spectral lines is the movement of electrons from one energy level to another. So we have movements from this energy level to E1, or from E1 to that energy level. Or we can have movements of electrons again from E2 to E1 or E1 to E2. So whenever there is a transition of an electron from E1 to that energy level, then a photon of light is emitted. That photon characteristic to the wavelength associated with that. Remember, E is equal to hc over lambda, and that energy that is associated with that wavelength, that's the photon that's going to be emitted in the process. Similarly, when in the absorption process, we have also a photon of light being absorbed because of that process. So the energy that is going to be released is equal to that. So the general formula there is E2 minus E1 is equal to HF. So the energy of the photon is equal to HF. It's principle of the energy transition from E2 to E1. So the angular momentum, that is MVR, of the electron is quantized, i.e. does not have a continuous range of values. Only single values that are allowed, that is these E2, E1, E0 and so forth and so on. There is in between there, it's not allowed. This is a forbidden transition. So only allowed transitions give rise to these releases of photons. So that's what we mean that angular momentum of electron is quantized. This meant that the electron could only orbit at a certain radii and could only have certain values of energy called energy levels. There were no allowed states between these energy levels, and electron remains in an energy level without radiating energy. Bohr also proposed that an electron can jump from higher energy level E2 to a lower energy level E1 nearer the nucleus and radiate a photon of frequency f given by E2 minus E1 is equal to hf, where h is Planck's constant. The ground state is when an electron is in the lowest allowed energy level. This is the most stable state. The electron normally occupies this level. An electron which absorbs energy, e.g. by absorbing a photon of sufficient energy or by collision, will jump to a higher allowed energy level. The atom is now in an excited state. The excited state is unstable, and then the electron returns to the ground state by radiating a quantum of energy equal to the energy difference in the energy level again. The falling back can occur in one jump or in different steps from one energy level to another. Energy levels are labeled by quantum numbers n. The lowest energy level n is equal to 1, followed by n is equal to 2, is equal to 3, up to n is equal to infinity. N is equal to infinity is called the ionization level. By convention, the energy of a free electron outside the atom is taken to be 0. So all energy levels are negative values. So when we attain this ionization energy state, it will be 0. The rest are minus. So when we have a jump, that is a transition from say minus 300 to 0, then we are getting to the ionization state. Then from the ionization state, remember, it then leaves this. Let's further clarify this by looking at the energy transitions of the electrons. We will look at hydrogen as an example. Hydrogen spectrum contains distinct groups of lines. The most obvious groups are the Lyman series, the Balmer series, and Paschen series. So Lyman is the first one that you see there, followed by Balmer, then followed by Paschen, and then there's fund that we are not going to talk about. We just talk about Lyman, Balmer, and series. So the transitions from the ionization state to n is equal to 1 is in the Lyman series. Then followed by that, all transitions that go to n is equal to 1 are in the Lyman series, and all transitions that end at n is equal to 2 and in the Balmer, and n is equal to 3, and so forth and so on. Please take note that the energy level diagram sideways will give a diagram that represents the line spectra. So the energy levels, as you can see, they've been presented in EVs. Remember, 1 EV is 1.6 times 10 to the power of minus 19 joules. So these are minus and then to 0, which is the state. So which means the ionization energy of hydrogen is minus 13.6 times 1.6 times 10 to the power of minus 19 joules. So you need that energy to be supplied to the electron so that it can escape. So Lyman series, as we have said, corresponds to electron transitions to the ground state, n is equal to 1. Energetic photons in the UV region in the spectrum are given out. So this is beyond the visible range. In the Balmer series, electron transitions are to the first excited state, which is n is equal to 2. Visible photons are given out. So here we have some in the visible region. The line of the Paschen series are in the IR region and correspond to transitions that is to the n is equal to 3 state. So these we cannot see with our natural eye. The lines of the hydrogen spectrum fit the general formula F is equal to C R subscript H, then 1 over m squared minus 1 over n squared, where C is equal to 3 times 10 to the power of 8 meters per second. R subscript H is called the Rydberg constant, which is given that value 1.09678 times 10 to the power of 7 meters per second. For the Balmer series, you start off with m is equal to 2, then n is equal to 3, 4, 5, 6, and so forth and so on. Then for the Lyman series, m will be equal to 1, and then n is equal to 2, 3, 4, 5, 6. Then Paschen series, m will be equal to 3, n will be equal to 4, 5, 6, 7, something like that. So we have this one example to show. Calculate the energy released and the wavelength of frequency of the emitted radiation when an electron falls from n is equal to 4 to n is equal to 2. Right, so from n is equal to 4 to n is equal to 2, n is equal to 4, the energy level there is minus 0.85 EVs. Right, and then to n is equal to 2, which is minus 3.39 EVs. So we're going to say E2 minus E1. Right, so E2 is this one, minus 3.39 times 1.6 times 10 to the power of minus 19 minus 0.85 times 1.6 times 10 to the power of minus 19. So that should equal HF. So that's the energy anyway. So you just get the energy. You don't equate to HF. So that difference, they convert that to joules. That's the energy. Then says the wavelength and frequency. So we want to find the wavelength. We then say E is equal to HC over lambda. So you get lambda there. After getting lambda, we can say HF. Then divide this value there by Planck's constant to get the frequency. So they've worked it out for you. So they are, so minus this, minus like that, exactly like I showed you. You get that. Then HF, so we divide by Planck's constant to get F. And also you can use HC over lambda to get, make lambda the subject to get lambda there. And then also an example to apply the Rydberg equation is given there. Use the Rydberg equation to find the frequency of an electron transition from n is equal to 4 to n is equal to 2. Now we apply that, so that would be F is equal to C, Rydberg constant, 1 over m squared minus 1 over n squared. So that is that. Simple as that. So you just apply the quantum numbers there. Then we also have an example of the absorption spectra. An electron absorbs a photon which raises it from n is equal to 2 to n is equal to 5 state. Find the wavelength and the photon absorbed. So again, E2 minus E1 is equal to HF. So E2 minus E1, you then get the resultant there, and then we convert that to joules, you get that value. To find the wavelength, you just say HC over lambda is equal to that. So then make lambda the subject, you get that. Then an example on the ionization energy. Calculate the speed of an electron that would just ionize a hydrogen atom that was initially in its ground state. So from ground state, that is n is equal to 1, to ionization state n is equal to infinity. So remember, from ground state to n is equal to infinity, the energy is minus 13.6 EVs. So it's from, that is E2 minus E1. E2 is the ionization state, which has a value of 0. And then E1 is that value there, which is n is equal to 1. So 0 minus 13.6, then multiply by elementary charge to convert to joules. You get 2.176 times 10 to the power of minus 18 joules. Now if then equate this, because this is the energy that's going to be supplied to give the kinetic energy. So that kinetic energy is equal to that ionization energy. So which is going to equal to half mv squared, and then make v the subject of the formula. That should give you 2.2 times 10 to the power of 6 meters per second. Please give it a try. Let me know in the comments if ever you need help in the calculation of any of the questions that I've raised as examples. In my last video, I'm going to talk about the band theory. Signing out.